Hello, my dear. Let's see you again, and let's start our lecture number 6 on avionics engineering. And today we will be continuing the topic of previous lecture called fly-by-wire flight control. So let's start. The term control laws is used to define the algorithms relating the control surface demand to the pilot stick command and the various motion sensor signals, and certainly the aircraft height, speed, and Mach number. As an example, a very simple basic pitch rate command block would be as a top expression, where a eta sub d is the tailplane demand angle. Theta sub I here is the pilot's input command. Q here is the pitch rate. K capital is a forward loop gain. And the last component in this equation, G sub Q, is a pitch rate gearing. In practice, additioning control terms from other sensors like incidence and normal acceleration may be required. The value of K and the sensor gearings would also almost certainly need to be varied with high and air speed by an air data gain scheduling system, as already mentioned some second ago. Okay, control terms proportional to the derivative or rate of change of error and integral of error are also used to shape and improve the closed loop response. A brief explanation of the action of these control terms is given below and will be certain later in view of their importance in closed loop flight control system. Proportional plus derivative of error control provides a phase advance characteristic to compensate for the lags in the system. For instance, actuator response, and hence improve the loop stability. This increases the damping of aircraft response and reduces the overshoot to a minimum when responding to an input or disturbance. The control term is filtered to limit the increase in gain and high frequency, and smooths the differentiation process, which amplifies any noise present in the error signal. And this slide illustrates the gain and phase versus frequency characteristics of a simple filter, one plus derivative error control, usually known as phase advance control, with a transfer function, as you may see on the second row of the top this slide. The characteristic being plotted for n equal 3, 5, 7, and 10. And you can see as in left on the gain, 10, 7, 5, 3, and the non-dimensional frequency with the phase lead for 10, 7, 5, and 3. The amount of phase advance is determined by the value of n and is generally limited by the resulting increase in gain at high frequency and avoiding exciting structural resonance modes. Typical values used for n are between 4 and 5, a maximum phase lead of about 40 degrees. A more physical explanation of the damping action of a phase advance element is shown in this diagram. And this shows how a control moment, which is proportional to the error plus rate of change of error, suitably smooth, changes sign before the error reaches zero, and hence applies a retarding moment to decelerate and progressively reduce the velocity before the error reaches zero, and hence minimizes the overshoot. Proportional plus integral of error control eliminates steady-state error and reduces the following line. The integral of error term increases the loop gain at low frequency, up to theoretically infinite gain at DC, so that there are zero steady-state errors due to out of trim external moment of forces acting on the earth. The error when following a low frequency input command is also reduced and is zero for a constant input rate. The need for an integral term control can be seen by examining the simple system shown in this slide. In the steady state, if the theta sub I is constant, the theta sub 0 must also be constant. And thus, the resultant moment acting on the aircraft must also be zero, and the control surface moment is equal and opposite to the out of trim moment. However, to generate a control surface moment requires an error signal so that the theta 0 will be get here cannot equal theta sub I, cannot exactly equal. The magnitude of the steady state error is dependent on the loop gain K, as you can see here in this one, which in turn is limited by the loop stability. The effect of the proportional plus integral error of the error is not zero and reaches a value sufficient to generate the necessary control moment to balance the trim moment. The value of integral term control can thus be seen in achieving automatic trimming of the control surfaces. And this figure illustrates the gain and phase versus the frequency characteristics for proportional plus integral control. The transfer function let's look at this second expression on the top. It can be seen that the gain approaches unity at high frequency and should be equal 0 decibel with 0 phase shift, and so that the loop stability is not degraded, providing the integral time constant here is mentioned as a T capital and is suitably chosen. It should be noted that integral terms need to be initially synchronized to the initial conditions defined at startup to avoid large transients on the switch on. Mention has already been made by the carefree maneuvering characteristic that can be incorporated in FBW system. I hope you remember FBW, this term, yes? Fly by wire. This is achieved by continually monitoring the aircraft state and automatically limiting the authority of the pilot's command input by means of a suitable control law, which takes into account the aircraft's maneuver boundaries and control limits. This prevents the pilot from attempting to maneuver the aircraft into an unacceptable attitude or approach too near to the limiting angle of incidence or exceed the structural limits of the aircraft in a maneuver. A block diagram of a pitch rate command FBW flight control system is shown in this diagram. The essential redundancy has been omitted for the client. So the primary feedback of pitch rate for the pitch rate command loop is provided by the pitch rate by gyros, so that it's the lowest part. In the case of an aerodynamically unstable aircraft, an integral of pitch rate term is also used to provide a quasi-incidence term to counteract a positive and so unstable M sub alpha. It's next line, incidence sensor. The relationship between alpha and Q, between alpha and Q dt can be seen from the second equation. And the frequency response of the alpha over Q transfer function, in fact, approaches that if a simple integrator at frequencies where omega T2 many times higher than 1. In this case, the gain approaches is 1 over omega, and the phase minus 90 degrees. And hence, we have the Q times dt, it's approximately equal alpha for values of omega, such as omega T2 many times, much more times higher than 1. So the proportional plus integral control is generally applied to the pitch rate error. In this case, the Q times E will be proportional to the Q times D capital minus Q. Here I mean the Q times D capital, it's a demanded pitch rate. And this has the advantages of eliminating steady state following error and enabling the pilot to change the pitch attitude easily. But it should be noted that as far as the loop stability is concerned, there is no difference between placing the stabilizing transfer function in the pitch rate error path as opposed to the pitch rate feedback path. In the case of an aerodynamically unstable aircraft, a well-designed 1 plus integral of pitch rate error control can provide an acceptable stable loop. Also not an optimum one, without any other sensor terms, such as airstream incidence or normal acceleration. And this has the advantage that the key motion feedback sensors, namely the pitch rate gyros, are very rugged and reliable devices. Solid state rate gyros are very reliable sensors with an MTBF in the region of 50,000 up to 100,000 hours. So feed and forget device. And this is very nice. It should be noted that while airstream incidence sensors can also provide the stabilizing term to counter the unstable M times alpha, they have two inherent shortcomings as far as the core stabilizing function is concerned. And in this case, we have several conditions. First condition, vulnerability to damage on the ground or bird strikes in flight, as the sensors have to be mounted externally in the aircraft. B, problems in matching due to the differences in the local airflow at the different locations. So like two sensors located on the forward side of the fuselage and two sensors on the starboard side. The incidence term from the airspeed sensor can be blended with the pitch rate error term, and the carrying or gain coefficients of these terms adjusted as higher angles of attack are approached. This enables the angle of incidence to be kept within the safe limit whilst maneuvering at high angles of incidence or angle of incidence limiting. Normal acceleration terms from the normal accelerometers are also blended with the other control terms, and the gearings of the terms adjusted at high normal acceleration are demanded so as to give normal acceleration limit. The blending of normal acceleration and pitch rate is sometimes referred to as C times M, star control. The blending of pitch rate and normal acceleration to meet pilot handling criteria is, however, a more complex subject and beyond the scope of our lecture. Sufficient to say that optimal handling requires a blend of control terms, the mixing of which needs to be adjusted over the flight envelope. Air data gain scheduling is necessary to adjust the gearings of the control terms to cope with the changes in control effectiveness over the flight envelope, as explained a bit earlier. So far, the aircraft has been treated as a rigid body to deriving the dynamic response, so that it will be moving in their direction. So, in this case, the aircraft structure, however, is flexible and has a variety of flexural and torsional modes. This diagram illustrates the first body bending mode of the aircraft, longitude plane. The frequency of this structural mode is typically between 8 and 15 Hz for a fighter or strike aircraft, and from 2 to 4 Hz for a large transport aircraft. There are also second and third harmonic modes at twice and 3 times the first body mode frequency, and possibly significant even higher mode. The being state plane or four-plane plane are rudder and rudder have structural, so flexural and torsional vibration modes on their own, which couple with the aircraft structure. So the FCS sensor, which sends the aircraft motion, also sends the structural deflection, and hence couple the structure modes into the control loop. The location of the motion sensors with respect to the nodes and anti-nodes of the structural modes is important. In the example shown in this figure, ideally, the pitch rate gyros would be located on the anti-node, namely direction of the gyro input axis is unchanged, and the normal accelerometer on the node where the zero linear displacement, right? In this context, the best location for a normal accelerometer is the forward node because it reduces the non-minimum phase effect of the control loop. Are you agree with me? Okay, nice. The ideal locations, however, may not be practical and acceptable compromise have to be made on the sensor location. For instance, modern strap-down inertial measuring units require the gyros and accelerometers to be co-located in a rigid block. The compromise position is usually between the forward structure node and the central anti-node. The structural modes can be excited in 2 ways. First, inertially, it means through the inertial forces resulting from the offset of the center of mass of the control surface from the hinge line. And these forces are directly proportional to the angular acceleration of the control surface. And second, aerodynamically. In this case, through the changes in the aerodynamic pressure distribution over the control surface and adjacent surfaces when the control surface is deflected from its datum position. These forces are proportional to the deflection of the control surface and the dynamic pressure. It should be noted that the inertial excitation forces are in antiphase with the aerodynamic excitation forces, as the angular acceleration of the vibrating control surface is 180 degrees out of phase with the angular deflection. So both components are taken into account in assessing the structural coupling effect. Inertially induced excitation forces are predominant at low airspeed in the case of all moving control surfaces such as tailplane. The aerodynamic excitation forces are large and dominant at high airspeed in the case of relatively lightweight, but aerodynamically powerful wind trailing edge control surfaces such as ailerons and can excite the wing structural motion. It is thus necessary to attenuate the FCS loop gain at the structural mode frequencies to avoid deriving the surfaces at this frequency and exciting the flexible mode. This slide illustrates the frequency response of a typical notch filter, so-called because the gain versus frequency graph has a notch shape. The carriage of external stores and the fuel state produces significant changes in the model frequency and must be taken into account in the notch filter and FCS loop gain. The phase lag introduced by the notch filter at frequencies below the notch frequency has a destabilizing effect on the FCS loop. A worked example for a pitch rate command loop for a hypothetical FBW flight by wire, agile fighter with a 12% negative, it means unstable static margin, is set out below. It is stressed that the aircraft is a hypothetical one based on published data on several modern fighter aircraft and order of magnitude estimate. Okay, I mean, you understand it's combined from different model flights. Because the transfer functions in this example have been expressed in terms of the Laplace operator S by substituting S for the operator D capital over the D over dt to conform with the normal control engineering problem. The use of Laplace transform has many advantages in dealing with the initial conditions in higher order differential equations. And the persons that not familiar with Laplace transform will find them covered in most engineering mathematics textbooks or directly from internet now. So the beam incidence over G at 600 kilonewtons equals 2 over 3 degrees per G. Static margin equals 12% negative. Pitching moment derivative due to the control surface deflection, mu eta, equals 5 times 10 in power 6 Newton-meter per radian. And pitching moment derivative due to the pitch rate mq equals 5 times 10 in power 5 Newton-meters per radian per second. So we have the next problem. From the data above derived, a suitable pitch control law, neglecting lag in the actuator response, nonlinear effect, structural resonance, notch filter, etc. The stages in the proposed solution are set out now. And we start with the stage 1, derivation of Q over eta transfer function of basic aircraft. In this case, derivation on T1 and T2, you may see at this equation here. And as you know, T1 equals half second, and in this case, the half second. And given 2 over 3 degree being incident at 600 kilonewtons, as you see for the next equation for Z alpha, it gets us 16,000 newtons per radian. This we should be not only time in 10, it should be 10 in power 7. So be careful, it might fall here. It would be 10 in power 7. All these expressions measured in Newton per radian. Okay? And T2 equal, as you remember, 0.33 seconds. Derivation of MIA aerodynamic mean for C equals the beam area over beam span. It gets us 50 over 11. That gets us C 4.5 meters. Static measurement is a distance between center of gravity and aerodynamic center over the aerodynamic mean chord. In our case, it equals 12. And distance between center of gravity and aerodynamic center, it gets us, you can see here, it's minus 0.12 times 4.45. It gets us minus 0.54 meters. MA, proportional ZA times distance center of gravity to aerodynamic center, and get us this expression measured in Newton meter over radian. And the block diagram representation of the basic aircraft dynamics is shown in this diagram on the bottom part of our slide, with the numerical values of Mach number, eta, mu, q, m, alpha, T1, T2 in circle. The q over eta, as you can see here on the center of this slide, is obtained using the block diagram algebra. And let's see at this expression here. The response of the basic aircraft to a disturbance or a control input is divergent with the divergent exponential component with a time constant of 1 over 3.5 or 0.32, and hence time to double amplitude get us 0.22 seconds. And after that, we came to the next stage 2, derivation of stabilizing transfer function. This pitch rate demand loop and can be stabilized by a control with a transfer function GQ. As in this slide, we have as a GQ, and where the GQ is a controller gearing, degrees control surface moment per degree per second pitch rate error. T capital here is the integrated time constant, and QE is the pitch rate error. The overall loop is shown in block diagram at this figure, at the bottom part of our slide. The open loop transfer function is Q over QE. The closed loop transfer function is Q over QD. Equating the coefficient of S2, S, and the constant term, and substituting as the theta as a 0.6 and omega naught at 6.3, yields as next third equation here. And so these 3 simulation equations for the 3 unknown T, Q, T, and give us GQ get us 0.46 degrees control surface per degree per S pitch rate error. T capital equals 0.105 seconds, and A, it get us 6.58 1/2. The transient response to a disturbance of control input is thus made up of a subsidence with a time constant of 1/6.58. That is, get O.15 seconds and O.6 critically damped sinusoids with an undamped natural frequency of 1 Hz. Damped natural frequency is 5 radians per second, or 0.8 Hz, and that is far well-damped response. The work example has been very much simplified by ignoring the lags, which are present in a real system, and by assuming a rigid aircraft. The object is to illustrate basic principles, and in particular, the use of a proportional plus integral of pitch rate error control law to stabilize an aerodynamically unstable aircraft. The design of a flight-by-wire flight control system must take into account all the sources of lags, which are present in the control loop, and accurately model the structural coupling effect on the flexural modes. Lags in any closed-loop system are destabilizing, and the significant sources of the lags are actuators, sensor dynamics, and noise filters, latency in the computational processes, and notch filters. These effects are briefly discussed as follows. Actuator response. The response of the actuator at low frequency is basically that of a low pass of first-order filter. But as the frequency increases, the lags in the first stage actuation system become not dominant. The output or input ratio falls at an increasing rate, and the phase lag rapidly increasing, and the frequency response of a typical flight-by-wire actuator is shown in this figure. Phase lag at 1 Hz is in the region of 10 to 12 degrees. At 5 Hz, at 5 Hz, as you can see, around 50 degrees. At 10 Hz, the lag is the region of 90 degrees, and the output-input ratio has fallen to nearly minus 6 decibels, approximately 0.6. And it should be noted that a full dynamic model of a typical fly-by-wire actuator, FBW, is around an 11th order system when all the elements are taken into account, including the effect of compressibility in the hydraulic fluid. The response can, however, change very suddenly if rate limiting occurs, and the actuator can display a sudden large increase in phase lag, as shown in the dotted lines in this figure. Rate limiting can occur when the control valve travel limits are reached under conditions of large amplitude demand. The behavior under rate limiting conditions is nonlinear, and the onset and the offset are dependent on the amplitude and frequency of the input demand. If rate limiting is encountered, say during extreme maneuvers, the resulting additional phase lag in the actuator response can lead to a severe temporary reduction of the AFBW loop stability mark. Potential handling difficulties can then occur as a consequence. Particular care is therefore taken in that design stage to avoid rate limiting effect in extreme maneuver. The control valve force and valve travel need to be adequately sized sensor dynamics. The sensor dynamic response may need to be taken into account, depending on the type of sensors used. For example, angular momentum rate gyros of the two axes dynamically tuned type DTG and have torque balance loops with a bandwidth in the region of 60 to 70 Hz. Solid-state micro-machine quartz tuning fork rate gyros also have a bandwidth in the region of 60 Hz. The phase lag at low frequencies with such sensors is fairly small, about 5 degrees at 5 Hz, but may need to be taken into account if there are higher frequency structural resonances present. Noise filters may also be required on the sensor output. These filters also produces phase lag. Next characteristic, latency. This effect arises from the use of digital computers in the processing of the control loss and sensor data. It results from the two effects, either of which cause a time delay and hence a phase lag. This effect, I simply delay the sensor data is sampled intermittently. And a transport delay, there is always some delay between when the computations are carried out and when the results of the computation are passed onto the actuator. This graph illustrates the phase lag produced by a sampling delay. The mean time delay is half the sampling period. The path lag produced by a time delay is directly proportional to frequency and is equal to an angular frequency multiplied by the time delay. For example, a time delay of 10 milliseconds produces a phase lag of 7.2 degrees at an input frequency of 2 Hz. At 10 Hz, the lag is 36 degrees. The amplitude, however, is not attenuated as the frequency increases, as in the case with a simple lag filter, and so the destabilizing effect is worse. Another characteristic, notch filter. The frequency response of a typical simple notch filter is shown in this figure on the right part of this slide. Note the rapidly increasing phase lag as the notch frequency is approached. This is followed by a rapid change to a phase lead above the notch frequency, which reduces to zero phase shift as the frequency increases and still faster. An appropriate example on the effect of the FCS loop stability from the phase lags produced by the several notch filters is shown on a Nickol's chart. And Nickol's chart in this graph, together with the effect of a phase advanced element. Nickol's chart show an open loop gain and phase at particular frequencies and enable the gain and phase margins to be read all time. The gain margin is the amount the loop gain and can be increased before instability results because the open loop gain at the frequency where there is 180 degrees phase lag has reached 0 decibel in unity. Typical gain margins are around 9 decibel. The phase margin is additional phase lag, which will cause instability by producing 108 phase lag at the frequency where the open loop gain is 0 decibel. Typical phase margins are around 45 degrees. But it should be noted that the phase of a highly damped structural resonance changes very rapidly from the near zero just before the resonance frequency to minus 180 degrees, just above the resonance frequency, being minus 90 degrees at the resonance frequency. The order of the system is greatly increased by the structural resonances and notch filter, so that the phase exceeds multiples of 360 at higher frequency. The phase of an nth order system reaches n times 90 degrees. Modern fly-by-wire agile fighters can have up to 80th order longitudinal control loop when all factors are taken into account. In order for the loop to be stable at the structural resonance frequencies, the open loop gain must not be exceeded from 0 decibel, where the phase is minus 180 degrees, plus multiples of minus 330 degrees. That is minus 540 and minus 900 and maybe etc., as well as minus 180 degrees. And adequate main you may see in this phase on the second part here on the right. So an adequate gain margin of, say, 9 decibel is required at this frequency. Structural resonance frequencies where the open loop phase lag is minus 130 degrees or multiplies minus 130 can be exceed 0 decibel. Gain for this frequency. And the action of the loop is to suppress this frequency. Clearly, the open loop phase as well as the gain must be known as the structural resonance frequencies under all circumstances. If phase stabilization is being relied on, the alternative is to require an adequate gain margin, say 9 decibel, at all the resonant frequencies and not rely on an accurate knowledge of the phase. A roll rate command system is shown in this slide. The primary feedback term being roll rate from the roll rate chart. Other sensors are also used to control the rudder automatically to counteract and suppress the lateral cross-coupling effect. A yaw rate R feedback term derived from the yaw rate gyros provides the yaw auto-stabilization function. Other terms can include yaw incidence angle beta from yaw incidence sensor, a lateral acceleration from lateral accelerometer. As in the pitch rate command loop, air data gain scheduling is used to adjust the gearings or gains of the control term. Derivative and integral terms may also be used. Notch filters are also used to attenuate the loop gain at the structural resonance frequencies. The control of the aircraft's flight path by the pilot can be represented as a closed loop process as shown in the block diagram at this graph. The pilot is an integral part of the outer loop in series with an inner loop comprising the RCS and aircraft dynamics. The pilot controls the pitch attitude and bend angle through the FCS so as to change the magnitude and spatial direction of the lift force vector. The lift force vector acting on the aircraft then produces the desired change in the aircraft's flight path through the flight path kinetics. The loop closure is through the pilot sensing. The matching of the aircraft response to the pilot's response thus determines the aircraft handling or flying characteristics. Good handling qualities can be defined as those characteristics of the dynamic behavior of the aircraft, which enable the pilot to exercise precise control with low pilot workload. The achievement of good handling characteristics is a major objective in the FCS design. The quality of the handling characteristics and the pilot workload are generally expressed in terms of the Cooper-Harpach scale of rating from 1 to 10. 1 being excellent and 10 the worst qualities possible. So they are positive where you have the rating. These ratings are derived from the pilot's comments in carrying out a range of tasks, which are defined in terms of flight phase categories A, B, and C. Category A consists of demanding, sorry, 1 second, please, low battery. Category A consists of demanding tasks, such as the air-to-air or air-to-ground combat and in-flight refueling. Category B covers fewer demanding tasks, such as climb, cruise, and descent. Category C covers terminal tasks, such as landing and takeoff. This table shows the Cooper-Harper scale of gradations for measuring pilot opinion. Deficiencies in the FCS design can result in what are referred to as pilot-induced oscillations, or PIOs for short, pilot-induced oscillations. These are sustained or uncontrollable oscillations resulting from the effort of the pilot to control the aircraft. They can have catastrophic results in extreme cases. This you may can find on the early test designed with F-22 Raptor. The phenomenon of PIO has been encountered in the aircraft since the beginning of a powered flight. The original Wright flyer is susceptible to PIOs in a conventional and augmented aircraft have generally been due to design deficiencies such as low damping or the short period pitch mode. For low control sensitivity, it means a stick force over G. With the advance of flying by wire aircraft with high gain feedback control systems, however, PIOs have generally been the result of some nonlinear events, such as rate limiting in the actuation system. Rate limiting can result in an abrupt increase in the actuator lag and consequent degradation and lag in the FCS response. PIOs were in fact encountered in early development flight testing on the Lockheed YF-22 fighter and the prototype Saab JAS-39 Gripen fighter, and also during early flight testing of the C-17 transport and Boeing 777. These have been attributed to rate limiting effects. But it should be noted, however, that the rate limiting does not necessarily result in PIO, and the methodology of predicting PIO susceptibility, particularly following a nonlinear event, is not yet at a major stage. Analyzing the effects of nonlinear behavior in an element in a control loop is very much complicated by the fact that the response of the element is nonlinear and is dependent on the frequency and amplitude of the pilot's lead. The subject of handling characteristics and PIO involves very considerable background knowledge, and it is only possible within the space constraints to give a very brief overview. The control exercise by the pilot is influenced by the following factors. There is an inherent time delay of the order of 0.3 seconds in the pilot's response. The pilot's control sensitivity or gain, however, can be varied, and the pilot is able to provide a phase lag to compensate for the aircraft's response. In reality, yes. Or as a smoothing lag filter response is required, and the pilot's bandwidth is of the order of half Hertz. And in this case, should be noted that the pilots dislike having to apply lead or lag because the resulting increase in workload. So they should compensate it. So anytime. Consider now the pilot as a part of closed loop control system. There are many lag elements in the outer control loop, comprising the pilot and the FCS or airframe combination, and the phase lag around the loop, and reaches and exceeds 108 degrees as the frequency is increased. It can be seen that, as in any closed-loop control system, increasing the gain exercised by the pilot at the 800 watt frequency and will result in the loop going unstable if the loop gain reaches unity. And hence, if the pilot increases his gain in an attempt to get tighter control and overcome a lag in the aircraft response, the consequence can be that the aircraft becomes more out of control. The pilots get out of phase, and the harder the pilot works to control the aircraft, the worse the situation becomes, and the PIO's result. References on the subject of handling characteristics are given at the end of my hard copy of this lecture. Or you might directly ask it in my email. The treatment of closed-loop flight control systems in our lecture has used the classic linear control theory approach. The aircraft dynamics have been simplified whether possible to enable a good basic understanding to be obtained, for example, simplifying the pitch dynamics to a second-order system transfer function by assuming the forward speed is constant over the short period motion, deriving the roll rate response to aileron movement by assuming pure rolling motion, and neglecting roll and yaw cross coupling effect. Similarly, the short period yawing motion is first derived assuming pure yawing motion, and the yaw or roll cross coupling effect neglected. The representation of the system dynamics and the control processes in the form of matrix array of first-order equations is a key feature of what is now referred to as modern control theory. Flight control systems come into the category of multi-input or multi-output MIMO closed-loop control systems, as control is exerted about 3 axes and there are 6 degrees of freedom. The classical control theory approach is very suitable for single input or single output SISO closed-loop control systems, and some single input multiple output SIMO systems like 2 outputs. However, modern control theory has been specifically developed to deal with MIMO systems and is now widely used in the design of modern flight control systems. The techniques are very powerful and can deal with the non-linear systems. The methods, however, require a good understanding of matrix algebra, and not all readers or our students familiar with this subject. But generally speaking, it's not difficult. It's only understanding this expression. For this reason, the classic control theory approach has been considered more suitable for our lecture, as it is intended to act as an introduction to what is a large multi-discipline subject. It should also be stressed that classical control theory methods are extensively used in parallel with modern control theory methods because of their robustness and visibility in particular areas. Our next part of lecture is called redundancy and failure survival. Clearly, the fly-by-wire flight control system must be no less safe than the simple mechanical control systems which is replaced. The safety levels required are specified in terms of the probability of a catastrophic failure occurring in the system from any cause whatsoever, which would result in loss of control of the aircraft. It is generally specified that the probability of a catastrophic failure in the flight control system must not exceed 10 in power minus 7 over hour for a military aircraft, and power 10 in minus 9 over hour for a civil aircraft. So look at 3 times higher order. And these very low probability figures are difficult to appreciate and also impossible to verify statistically. To give some idea of their magnitude, a failure probability figure of 10 in power minus 9 over hour means that a fleet of 3,000 aircraft flying an average 3,000 hours per annum would experience one catastrophic failure of the FBW system in 100 years. Military aircraft utilization per annum is much lower than civil transport aircraft, so that a figure of 10 in power minus 7 per hour for the FBW system is accepted. What I might say? It should be noted that the statistical level of safety currently being achieved with civil aircraft transport corresponds to a figure of around 10 in power minus 6 over hour. And this figure is derived from the total number of civil aircraft crashes occurring in a year from all causes divided by the total number of aircraft flying and their annual operating hours. The mean time between failures of MTBF of a single channel F fly-by-wire system is in the region of 3,000 hours. The fly-by-wire system must thus process redundancy with multiple parallel channels so that it is able to survive at least 2 failures. If this very low failure probability figures out to be met, there is clearly an economic limit to the number of parallel redundant channels. Apart from the cost of the additional channels, the overall system MTBF is reduced, and hence the system availability is lowered. While it may be acceptable to fly this one failed channel, assuming sufficient redundancy, the impact on availability is obvious if the overall MTBF is too low. A well-established redundant configuration comprises 4 totally independent channels on sensors and computers in a parallel arrangement. To give the required failure survival capability, such a configuration is referred to as a quadruplex system. The 4 independent channels, 1, 2, 3, and 4, are then configured to drive a failure survival actuation system with sufficient redundancy, such as the overall fly-by-wire system of interconnected sensors. Computers and actuators can survive only 2 failures from whatever cause. And this figure illustrates the basic quadruplex configuration. The integrity of the electrical power supplies and the hydraulic power supplies is absolutely vital, and adequate redundancy must be provided so that the system can survive failures in both the electrical and hydraulic power supply. In fact, the starting point in the design of a fly-by-wire system is the safety and integrity and redundancy levels required to the electrical and hydraulic power supply systems, as their integrity dominates the overall FBW system integrity. With 4 totally independent channels, the assumption is made that the probability of 3 or 4 channels falling at the same instant in time is negligible. And this assumption will be discussed a bit later. And thus, if one system fails, cut over, another saying demanding maximum control surface moment, the other 3 parallel good channels can override the failed channel. However, to survive a second failure, it is necessary to disconnect the first failed channel. Otherwise, it would be stalemate, 2 good channels versus 2 failed hard over channels. so that the control surface does not move like a failed passive situation. I hope you understand me properly, right? And failures are therefore detected by the cross comparison of the parallel channel and majority voting on the odd man out principle. The quadruplet system is thus able to survive two failures by majority voting and disconnecting the failed channel. The system degrading to triplex redundancy after the first failure and duplex redundancy after the second failure. A third failure results in a failure passive situation, the good channel counteracting the failed channel. The incorporation of a moving system to check the correct functioning of a channel to a very high confidence level can also enable a failed channel to be identified and disconnected, and this leads to an alternative failure survival configuration known as monitor triplet. A monitor triplet configuration comprises three totally independent parallel channels, with each channel monitored by the dissimilar system to detect a failure. Provided this monitoring is to a sufficiently high degree of integrity and confidence level, such a system can survive two failures. The respective metrics of the two systems are fairly evenly divided. The monitor triplet system has rather less hardware and so can be of lower cost. This is offset by the better visibility in terms of failure survival confidence of the quadruplet system, particularly when it incorporates self-monitoring to a high confidence level. And this slide illustrates the quadruplets and monitor triplets redundancy configurations schematically. As already mentioned, failures are detected by cross comparison and majority voting. However, it is necessary to allow for normal variations in the outputs of the parallel sensors measuring a particular quantity due to inherent errors in the sensor and their manufacturing tolerances. Normal errors in sensors include such parameters as scale factor errors, linearity errors, null or zero offset errors, hysteresis errors, and vibration of the above parameters with temperatures and anomalies. The absolute accuracy of the sensor is rather less important, within reason, than the variation or tracking error spread between individual sensors, particularly under dynamic conditions. For instance, a situation where all the sensors were in error by nearly the same amount and the variations between the individual sensors were small would be preferable to a higher absolute accuracy, but a larger variation. Variations in the dynamic response of the parallel sensors must be small. For instance, consider two sensors measuring a sinusoidally varying quantity, but with a slightly different phase lag between the two sensors' output. The difference between these two sensors' output is a sinusoidally varying quantity of 90 degrees out of phase with the input quantity and with an amplitude directly proportional to these phase difference, as you can see at this slide. And thus, a phase difference of 2 degrees or 1/30 radian approximately results in a tracking speed over 3% of the peak value and the input quantity. And this result is arrived at as follows. Let theta 1 and theta 2 be the two sensor outputs measuring an input quantity theta. The first sensor having a phase lag p, phi, and the second sensor having the phase lag psi plus delta psi. And assume, for simplicity, that both sensors measure the peak amplitude theta maximum. Look at this on the graph. and without error. And thus, difference between two sensor outputs, as you can see in this expression, theta maximum times sine omega t minus psi minus theta maximum times sine from omega t minus psi plus delta psi, and approximately equal as the delta p times theta maximum times cosine between omega t minus psi. So the sensors should thus have a high bandwidth, and so that the phase logs at the aircraft control frequencies are small anyway, and the phase variations between the sensors will thus be very small. The variations between the filters used to filter sensor output noise are also minimized by using accurate, stable components in the filter. The failure detection algorithm enables the detection and isolation of a sensor whose output departs by more than a specified amount from the normal error airspeed spread. The value of this disconnect threshold in conjunction with the failure detection and isolation algorithm determine the magnitude of the transient with which the aircraft may experience as a result of the failed sensor being disconnected. There are thus two conflicting requirements. First, a low number of nuisance disconnections, and second, minimum transient on disconnecting a failed sensor. If the disconnect threshold is set too low, a sensor can be deemed to have failed and be disconnected when it is merely at the edge of its specification tolerance. Another saying, a nuisance disconnection. Conversely, if set too high, when a real failure does occur, the magnitude of the transient on disconnecting the failed sensor can be unacceptably large. Failures can be divided into the following categories. First, hard-over. Failures whereby the failed sensor output is hard over the full scale and would demand full authority control surface movement with catastrophic results. Second, zero output failures whereby the sensor output is zero and thus no control action would take place. And three, slow over failures whereby the sensor output is slowly increasing or drifting with time. Also, the input is stationary and would eventually cause a full-scale cutover. 4. Oscillatory failures whereby the sensor output is oscillating, the amplitude and frequency being dependent on the type of failure. Loss of feedback, for instance, can result in a stop-to-stop oscillation. 5. Soft failures, whereby the sensor is functioning, but its output is outside the specification tolerances. And 6. Intermittent failures, whereby the sensor fails and then recovers intermittently. For example, suppose full-scale sensor output is 100, and the normal sensor tolerance is plus minus 0.5%. The disconnect threshold is generally taken as 1.5 times maximal signal variation, and in this example would thus be equal to 1.5. It's our approximation. Suppose, for example, sensor outputs for a particular quantity were as follows: theta 1, 60, theta 2, 60.5, theta 3, 60.7, and theta 4, 59.7. The lower middle value is 60, and the differences of the higher and lower value sensor output from this middle value are 0.5 and 0.3 respectively, so that all sensors output would thus be valid. Consider now two failures examples. First, a hard over failure, and second, a slow over failure, as shown in this figure. After either of the above failures, of above failure, the system would be at triplex level, and the same two failure causes are considered for a second sensor failure, and are shown in this figure. The tasks carried out by each lane of a quadruplex system, and shown in this slide. A typical quadruplex system architecture is shown in this figure with votes and output consideration. The essential buffering and isolation of outputs, like electro-optic isolators, is omitted for clarity, but is essential to prevent electrical faults in one channel propagating into another for common mode failures. So, the use of two or more different types of microprocessors with dissimilar software. For use of a backup analog system in addition to the main digital system, which is at quadruplex or triplex level of redundancy. And third, use of a backup system using different sensors, computing and control means like separate control surfaces. And this slide shows a generalized dissimilar redundant flight control system architecture. Modern airliner design practice is to split the basic control surfaces into 2 or 3 sections, with each section controlled independently by its own actuator. The movement exerted by each section of the control surface are thus sound aerodynamically, and the failure of an individual section can be tolerated. This gives increased failure survivability to the flight control system. Most of the control surfaces are controlled by the two actuators, in some cases, dissimilar types of actuators. And this figure shows the flight control surfaces of an Airbus A380 airline. Roll control is provided on each wing by 3 ailerons, complemented by outboard spoilers. Pitch control is provided by the trimmable horizontal stabilizer THS and 4 elevators hinged on the THS. Yaw control is provided by 2 rudders. Yeah. A brief overview of the A380 flight control system is given to show the very extensive use of dissimilar redundancy and the ability to absorb failures. The Airbus A318, A319, A320, A330, A340, and A380 airliners share a common flight control system architecture with similar control laws. And this provides similar flight handling characteristics, enable easy cross-qualification across the range. The A380 flight control system is shown in this slide. 3 totally independent primarily PRIM, flight control, computer control, 1 set of ailerons, spoilers, elevators, and rudder. The autopilot is included in the PRIM. 3 totally independent secondary SEC, flight control, computer control, and second set of ailerons, spoilers, elevators, rudder, and the THS. Each computer is capable of controlling pitch, roll, and yaw axis through its associated actuator. Each computer comprises 2 independent processing channels with different internal architecture. The processors being produced from different manufacturers with their software generated by different teams. In the case of disagreement between the 2 processing channels, the computer is automatically disconnected. The A380 can be dispatched with any one of the 6 computers failed. Under normal control laws, the pilot exercises a maneuver command control through the side stick of a load factor for the longitudinal control and roll rate for lateral control. Inside the normal flight envelope, the main features are neutral static stability and short-term attitude stability, automatic longitudinal trimming, lateral attitude hold, and automatic elevating turn, Dutch roll damping, and turn coordination. Flight control protection, like load factor, angle of attack, speed, attitude, is also part of the flight control laws and provide the pilot with instinctive procedures to get maximum aircraft performance in emergency situations. Aircraft feedback is provided by the Air Data Inertial Reference System, ADIRS, and dedicated sensors, accelerometers, rate gyros, etc. The flight control functions are exercised through the PRIM and SEC computers as shown in this figure. One of the PRIM is a master computer and carries out the computation function. It computes the control surface deflection for the aircraft to respond the pilot or autopilot commands in an optimal manner from the appropriate control law, and the aircraft feedback from the ADIRS. The 3 PRIMs and the 3 SEC each carry out the execution function of control and monitoring of their assigned servo actuator, so that control surface deflections obey the computed dump from the master PRIM. The master PRIM also carries out self-monitoring and checks its commands are being executed by comparing them with the aircraft response feedback from the ADIRS. If a malfunction is detected, the master PRIM passes the computation function to another PRIM. The master PRIM may continue to perform the execution function depending on the malfunction. If all the PRIMs are lost, each SEC performs the computation and execution function. There is no master SEC. Progressive control law reconfigurations occur as a function of a system failure status and are indicated to the pilot through the following law. Normally law, in case as the auto trim control laws and flight domain protections available. Normal flight control law is available after any single failure of sensors, electrical system, hydraulic system, or PRIM. Alternate law. In this case, auto trim control laws and flight domain warning. Direct law, manual trim, direct relationship between side stick deflection and surface position, longitudinal and lateral stabilization, and flight domain warning. An electrical backup system provides control of the aircraft in the extremely improbable case of loss of all the flight control computers or electrical power supplies. The electrical backup system is totally segregated from the normal flight control system and uses dedicated sensors and transducers in the pilot control. The backup control module controls and monitors the inboard elevators, the THS, the inboard ailerons, and the upper and lower rudder on. Specific control laws apply whenever the electrical backup is active and provide pitch motion damping, yaw damping, and roll control. The THS can also be controlled from trim switches located on the pedestal. The fly-by-wire flight control system of the Boeing 777 also makes extensive use of the similar redundancy. This slide is a simplified block diagram of the primary flight control system architecture. The pilot's commands are transmitted directly to the four actuator control electronics, ACE, units, and are then routed through the ACE to the IAR INC 6 to 9 data buses. At the heart of the system, there are three identical digital primary flight computers, PFS. Each PFS forms a channel so that the three separate PFS provides three independent control channels in the primary flight control system. The PFS architecture is shown in set and comprises three independent dissimilar processors, which are physically segregated within the box. The software for the three processors being generated by independent groups to the same requirements specification. The system normally operates with one processor in each PFC in command and with the other two processors acting as monitors. The PFCS is able to absorb multiple random component failures or a combination of a software generic errors and random failures. And this slide illustrates the failure absorption capability. In the very unlikely event of the PFCS becoming totally inoperable, then a reversionally analog command path is directly available through the ACE to provide aircraft control. Each ACE also contains a solid-state pitch rate gyro for use when normal sources of body motion are not available to enable a pitch auto-stabilization function to be maintained. In addition to this backup mode, an independent mechanical link is also provided via the stabilizer trim system and a pair of flight spoilers. I think it's enough for now. Next lecture, we will be continuing our topic. And for this moment, I hope you enjoyed this lecture. And I'm looking forward to see you next time to continue this lecture topic. Bye.